Hickory dock, the mouse ran up the clock. The clock struck one, the mouse ran down. Hickory dickory dock. Hickory dickory dock, the mouse ran up the clock. The clock struck two and down he flew. Hickory dickory dock. The mouse ran up the clock. The clock struck one, the mouse ran down. Hickory dickory dock. Hickory dickory dock, the mouse ran up the clock. The clock struck two and down he flew.
Good afternoon. My name is Byrd. Thank you so much for coming. I realize some of you came with no power on at home. Maybe that's the reason you came. And I realize some of you only recently got your power, including the club, which until 9:30 last night we weren't sure what we were going to do. So we're pleased that they got their power and been such great hosts. I want to keep the introduction very short. All of us have heard, and soon will again, the Speaker of the House, in introducing the President at each State of the Union, say words along these lines. I have the high privilege and distinct honor of presenting. Well, I have the high honor and distinct privilege of presenting Lonnie Thompson and Mosley Thompson. How unusual it is to have a member of your family be a member of the National Academy of Sciences. Far more unusual to have two in one family, in one marriage, be members of the National Academy of Sciences. Amazing. I'll say that Lonnie also was a winner of the National Medal of Science, the highest award the U.S. government gives to a U.S. citizen for science. It was in 2005 under the George W. Bush administration. They have between them published hundreds of peer-reviewed articles. They have between them led scores of expeditions to the highest altitudes, whether it's in the Arctic and Greenland or in subtropics, Himalayas. They have revolutionized our understanding of climate change. Google them and see what incredible scientists and incredible contributions they've all made. If you get a chance and you'd like to read great books, read Thin Ice. Thin Ice by Mark Bowen. It's a terrific read, and it'll give you further insights into what it's like to go to the top with the Thompsons. With that, I'm going to ask Ellen to speak first, and they will both take questions. They'll both be here afterwards. Ellen Mosley Thompson.
Probably had plenty of time to look at the slides, but essentially what they're showing, if I turn this on, is some of the places where, I don't know what's going on, but there are some of the places where Lonnie and I have conducted the science, drilled the ice cores that we bring back to Ohio State, where we analyze them and then subsequently publish the results. So want to just also highlight our team. We have 12 permanent members of our research team. These are the senior personnel, and we currently have 5 postdoctoral scholars working with us. And our funding comes primarily from the National Science Foundation. We've been funded in the past by NASA, by NOAA, and most recently by the Volo Foundation. So what are the key points that we'll discuss today? Earth's climate is changing, the world is warming, and there's no debate. I hope when you walk out of here, you will realize that the Earth is warming. And all you have to do is look at the data. Global climate change involves many changes. It's not just temperature. We hear about temperature, but there's also changes in precipitation, Where the people here, you probably think quite a bit about sea level rise, ocean acidification, lots of ecosystem disruptions, melting glaciers. Lonnie's going to talk quite a bit about melting glaciers. That's one of the things that we specialize in studying. It's very important to realize that climate and weather are very different. Climate changes the changes to the Earth's climate system are driven by both natural and anthropogenic forcing. It's not all just human produced. The Earth's climate has been changing for millions of years. Glaciers can serve as both indicators and recorders of climate change. The rate of glacier loss is accelerating globally, and unique paleoclimate archives are disappearing. And Lonnie will close up with some of the greatest challenges for the 21st century. So let's look at the data. Earth is warming. Environmental conditions are changing. Just talk to your farmers. Talk to the people who work on the water. They'll tell you that things are changing. This is the global average land-ocean temperatures from 1880, for those in the back, 1880 up to 2007. That's this dot right here. Now, if this is the global average. Now, if we look at what the trend has been globally, since 1880, the Earth has warmed 1 degree centigrade. Keep that in mind, a warming since 1880 of 1 degree centigrade. But this shows that change has not been distributed equally across the planet. You can see there are areas, particularly the high Arctic, where the warming is greater. This is called Arctic amplification. It's fairly well understood. We can also look and see there are some areas where the trend has been cooling. But when we talk about global climate change, we're talking about global, we're not talking about local. I should point out that the last 4 years have been the warmest 4 years in this record. The climate of the last 40 years has been very remarkable. We've seen increased frequency and intensity of extreme weather. Heat waves, for example, particularly in Western and Central Europe, with 70,000 deaths. In Europe and Russia, fire and smoke, 55,000 deaths. We have these prolonged droughts now, and with drought we get fire. And then floods. We're seeing more flooding. And the interesting, not interesting, but, I think it's interesting, is that the Intergovernmental Panel on Climate Change models predict that these are exactly the type of system responses that we should expect. More extreme weather events, all right, and more frequent. So let's just for a second remember that climate and weather are different. What we're experiencing today, what you experienced over the last few days when you lost your power, is really weather. Now, I like this diagram because here is the man. He's walking his dog. This shows you the man's foot. This is his trail. So if you had to guess where the man is going, you'd probably guess that he's going up here somewhere. Yes, he could take off in this direction, but it doesn't look like it. Now, tethered to the man by the leash is the dog. And you can see the dog jumping all around. Fire hydrant, McDonald's wrapper, who knows what. But this is the dog. Most of you probably have dogs. You know how it works. So it's important to think about the man and the dog. And remember that the dog walker is the climate. Climate is really the statistics of the weather. And then the dog is the weather. Think of him jumping around. So Mark Twain is purported to have said, it's not been documented, that climate is what you expect and weather is what you get. So I looked up the weather in Richmond. It was the closest place I could find to here that had a 30-year uninterrupted climate history. And you can see that the average for February, the 30-year average, that's called the climatological mean, is about 41 degrees Fahrenheit. But if you think about this past February, it was a little warm. It was about 6 degrees warmer than the 30-year mean. And if you go back to 2015, the average temperature for February was almost 10 degrees colder All right? So now let's look at that distribution of temperature on the planet again. If you were living here, your perception in 2015 was that it was very cold. Same thing in Columbus, Ohio, where we're from. But in reality, it was the second warmest February on the planet. You can see here, for example, the jet stream configuration was like this. And here we are in the east, and it was very cold. Had you been in Alaska or in the western side, the Rockies here, it would have been very warm. Very warm in the northern part of Asia. You were getting the cold weather coming down from the Arctic here. This is what the jet stream would have looked like. And you were getting the warm weather coming up from the tropic in the west. So you can't look outside your window and you can't see global climate change on a day-to-day basis. If you've been in a place by 40 or 50 years and you notice changes, then you're probably seeing something with the climate and the environment. So the Earth is warming, we said, by 1 degree centigrade since 1880, so where's all that heat going? About 94% of it is going into the ocean. Remember that 70% of our planet is covered by water. The other 2% is going into the atmosphere and some into the land surface, much less into the glaciers. This shows the global heat content from 1920 up to 2016. You can see how that's increasing, and half of this increase has actually occurred since 1997. You can also see that we've got three colors here. This is more the surface of the ocean, the middle part of the ocean, and then what's called the deep ocean. That would be below 2,000 meters. Notice that even the deep ocean is warming. That means the warming at the surface is now being mixed deeper and deeper into the ocean. Any of you all live by the water. You know that what takes a lot of time for the water to warm up takes a lot of time for the water to cool down. So it has a very big heat capacity. What's happening in the Arctic? This shows the extent of Arctic sea ice extent since 1979, when we started observing sea ice using satellites. Yes, up and down, year to year, climate, more of the weather variability. But what's the trend? The trend tells you that by the end of summer every year, the extent of the sea ice is typically less. This right here is September 23rd, 2018. All right? So after the satellite flies within 5 days, NOAA has these data up. This is the lowest sea ice on record. That was 2012. What's happening to the Greenland ice sheet? You know that the Earth has two big ice sheets, the Antarctic ice sheet and the Greenland ice sheet. What we have here is almost a 30-year average showing you the cumulative melting of the surface of the Greenland ice sheet. Now this is just the thin layer. But so you can see that most of the melting over the last 30 years has been around the periphery and mainly to the south. Here is the cumulative melt days for 2012. I pointed that out. That was that year of the lowest sea ice. It was a very, very warm year in the Arctic. And look at the melting in the high Arctic around Greenland. Tremendous amount of melt. They had 5 days in July when 98% of the surface of the Greenland ice sheet was experienced some degree of melt. And this is more of a typical year. And you can see that we have much more melting now in the north than we had in the 30-year perspective. And then this is what the melting on the Greenland ice sheet would look like. These rivers just pour across the ice sheet. I took this photograph when I was flying from Sonderstrom up to the summit of the Greenland ice sheet a number of years ago. And you see these meltwater ponds? And then you can see how they're even connected by streams like this. And then every once in a while, they actually plummet down into a crevasse. So let's take a look at Antarctica. Now Antarctica is kind of the big gorilla, and that's where most of the ice on the planet resides. We have two ice sheets. This is the East Antarctic ice sheet right here. This is a mountain chain called the Transantarctic Mountains. This is a very stable ice sheet. In the center, it's up to 4 kilometers thick. and the bulk of it is grounded above sea level. What that means is it is frozen to the bed in most places, and that it's much more stable. This is the West Antarctic ice sheet, and it is very potentially unstable. It's what's called a marine-based ice sheet, so that where the ice and the bedrock come together is actually depressed below sea level, and that makes this unstable. And the greatest warming is occurring in West Antarctica. Now let's look at how much sea level rise equivalent you have. In the East Antarctic ice sheet, 60 meters of sea level rise equivalent. Don't worry about that. The East Antarctic ice sheet isn't going to melt anytime in the next century or two. But the concern is with the West Antarctic ice sheet because it's inherently unstable, because it's grounded below sea level. It has 5 to 6 meters of sea level rise. Now, this is two companion papers were published back in 2014 talking about this area of the West Antarctic ice sheet. Now, I won't go into a lot of detail, but essentially what is happening is these ice shelves that sit out in front of, like the Pine Island Glacier, the Thwaites Glacier, the Pope Glacier, etc. These ice streams drain the central part of the West Antarctic ice sheet. These floating ice shelves buttress or push back the ice that's on land. Remember, floating ice does not contribute to sea level rise. It's only the ice on land that's deposited into the ocean that contributes to sea level rise. And for geologic reasons, which I won't go into and I'd be happy to discuss later, essentially the take home from these two papers, one in Science, one in Geophysical Research Letters, is that this loss appears to be not only rapid but unstoppable at the moment. And these glaciers will continue to run their course until they reach a new steady state. What's happening to global sea level? Since 1880, you can see the rise in global sea level, but you kind of see three things here. The rate of sea level rise has changed. The shape of this whole curve represents the expansion of the ocean water. Remember, 70% of our Earth is covered by water. A lot of that heat is going into the water. The water expands and sea level rises. But early on, the sea level was rising at 1 millimeter a year. And then from about 1925 to 1992, it increased to about 2 millimeters a year for that. That's the average for that time period. What we're getting here now is the beginning of the loss of the mountain glaciers. The mountain glaciers are small, they're very sensitive. They'll be the first to go, as Lonnie will show you evidence. And now what's happening, we now have the ice sheets kicking in and contributing water to sea level rise. So sea level's rising 3.3 millimeters a year on average. And that will not stop. That's the bottom line. Sea level is going to continue to rise for quite a while. So I mentioned the fact that the Earth's climate is driven by both natural and anthropogenic or human-made causes. So the natural mechanisms that primarily force climate to change, number one and most importantly, is solar output. Changes also in the amount of volcanic aerosols in the atmosphere. We don't get volcanic eruptions very often, these big explosive eruptions. But when we do, the sulfate aerosols reflect incoming radiation from the upper atmosphere back to space. And that's a cooling mechanism. And then there's internal variability within the system, things that we really don't understand, such as the El Nino Southern Oscillation, or ENSO, or the mechanics of the major monsoon systems, and also North Atlantic Oscillation. I won't get into that, but that affects your climate here. And then we have human factors that also force the Earth's climate to change. And the most important of these is the change in the concentration of greenhouse gases, principally water, methane, and nitrous oxide, and in tandem with water, or in tandem with CO2, particularly water vapor. So this shows the increase in CO2. This is the Mauna Loa record from about 1958. This is actual measured data. Then back to 1860, these data have come from the air that's are trapped in bubbles that are preserved in ice cores, and I'll show you more about that. In addition, human activities emit aerosols and various particulate matter. So for example, when we burn coal, we generate sulfate aerosols. They have a cooling effect. Not exactly, but a very similar effect to the sulfate aerosols that are emitted by volcanoes. When we burn biomass or burn wood, we produce black carbon. And black carbon actually warms the planet. It absorbs more of the incoming solar radiation. And then they say, and I believe it's true, that experts tell us that human activity now moves more sediment on the planet than all the rivers of the world. And so we're constantly changing the landscape. So how do we know, this is probably one of the most important graphs I'll show you. How do we know that the human activity is affecting the Earth's climate? And so how do we separate natural and human influences on the climate? We have to use climate models. This is the what's called hindcasting. So this is 1900 to 2000, so essentially the 20th century. This is the globally average temperature, and that's this black line. That's known. We know that because we've measured that. And so the question is, can the models hindcast? Can they forecast backward and get this answer, which we know is correct? And what this shows that here in green, if we force the models only with the natural factors only, the things we know, what volcanoes erupted, for example, what's the CO2 emissions been, all that's known for the 20th century, you see that those models cannot reproduce the temperature record that the Earth has experienced. But if we factor in human factors, the additional CO2 from human activity, the burning of coal, the impact of aerosols, the changes in the hydrologic cycle due to land use changes, etc., we do a much better job of being able to reproduce what we know the history to have been. So I want to go back to that air that's trapped in the bubbles in the ice, and I want to talk for just a minute about an ice core that was drilled here at Dome C in East Antarctica. It's about 3 kilometer long ice core. For those of you up front, you can see these bubbles in the ice. And I won't go through the method if anybody's interested, but you essentially extract the air from the bubbles. It's a challenging process. Then you measure the concentration of all the different gases that are trapped in these bubbles. And what we have down here is a record of the CO2 concentration in the Earth's atmosphere from time now, time zero, back 800,000 years, so almost a million years. And down here we have the temperature record that we get from measuring the oxygen isotopic ratio. And what we have is the warm period now, the last 10,000 years, the Holocene. This is when modern humanity developed. We only began to grow crops 9,000 years ago. So we've developed in a very warm part of the Earth's climate history. But if we go back 20, 30, 40,000 years, 50,000, back to 120,000, that would be a time called the Eemian. In here, like where I live in Columbus, Ohio, we were under a 1 mile of ice that extended from Canada all the way to Chillicothe. And that's called a glacial stage. And what you're seeing here are periods when the Earth is warm, when the Earth has lots of ice, when it's warm, it has lots of ice. And there are 8 of those glacial interglacial cycles here. And now look at the concentration of CO2. The match isn't perfect. You wouldn't necessarily expect it to be perfect, but you can see that when the Earth was warm, the CO2 was about 100 parts per million higher. When the Earth was cold, it's about 80 to 100 parts per million lower. This is all natural. There's no human activity shown at all in here. And actually, this pulsing is well understood. And if you're interested in that, I can talk about it later. So where are we today? This year, we made it to 407 parts per million. So if we look backward, we can see, based upon the history of the concentration of CO2, we're well above the concentrations that occurred naturally over the last almost 1 million years. And here's another very important take-home message. Most people really don't understand the fact that the CO2 that's emitted today stays in the atmosphere for a very long time. So what we're working with is a problem that is it's tractable on a long time scale, but it is a very challenging problem. Why? Because we depend upon fossil fuels. We wouldn't have what we have without fossil fuels. Energy is absolutely critical. We have people on the planet, 1.5 million people, 1.5 billion people on the planet don't have access to electricity. I won't get on my soapbox because Lonnie will never speak about that. Ask me about it, we can talk some more. But I want you to remember that CO2 remains in the atmosphere for a long time, unlike methane, for example. So this is what the decay curve for fossil fuel CO2 looks like. So CO2 emitted today, you would have 100% of that, and we have the sequestering of carbon by the Earth's natural processes. In 100 years, 1/3 of the CO2 that's emitted today will still be in the atmosphere. And 1,000 years from today, 20% of the CO2 that we've put in the atmosphere today will still be there. So that's why this is a grand challenge. Now, we can look back to a time called the Pliocene 3 million years ago, and at that time, the CO2 concentrations were similar to the concentrations we see today. At that time, Earth was 2 to 2.5 degrees centigrade warmer, and sea level was 22 meters or 72 feet higher. So, changing gears again, we need to know about our climate history. How do we know about what's transpired in the past? Well, there are many different systems on the planet that sequester, or, well, sequester is a good word, they preserve the Earth's climate history. Ice cores, that's what we do. Tree rings, corals, pollen that we find in lakes tell us about the vegetation. Speleothems, which are cave deposits, stalactites, stalagmites, and the ocean and lake sediments. They all contain very valuable information that allow us to reconstruct Earth's climate history. We're going to focus on ice cores because that's what we do. So just want to point out that ice cores are very powerful contributors to what we call multi-proxy reconstructions. Just a big word, and what that means is you need lots of records from different recording systems to get the full picture. Ice cores are great, but we don't have ice cores at sea level in the tropics. Lonnie will show you we have ice cores in the tropics, but you have to go to over 20,000 feet to collect them. And so what can we learn from ice cores? All this. We measure isotopes, we get temperature. We measure the chemistry of the ice, we get the chemistry of the atmosphere. We can measure the net accumulation when we have annual layers, such as this, which is from an ice core in northwestern Tibet. We measure the dustiness in the ice, we see the dustiness in the atmosphere. We can pick up past periods of desertification, of when we have deserts. Vegetation changes, volcanic history, anthropogenic or human emissions. And now we have a program where we're looking at entrapped microorganisms. What we find is that these microorganisms can be preserved thousands to tens of thousands of years in this ice. Just two examples. These are not nice examples, but this is, I will show you the graph, and it's a composite of these 5 ice core records from Greenland. This is excess sulfate. This is sulfate, this would be human-produced sulfate. We've taken out the sea salt sulfate, the volcanic sulfate, and this is 1800 up to 2000. You can see pretty stable up to around 1900, and this is the increased combustion of coal. Look at the additional excess sulfate in the Earth's atmosphere. But also note that it peaks right around 1970 and now has been coming down. Part of that is the Clean Air Act, enacted in 1963 and then strengthened in 67 and 1970. So the point is that when we recognize a problem, we do have the potential to do something in the right direction to try to ameliorate that. This is nitrate, and same 5 cores, same time slice, but notice it's pretty flat up until about 1950. Well, what happened around 1950 into the World War II, right? Also, we began to use more automobiles. Think back, I learned to drive on the one car that served, 4 people. That was a 1948 Plymouth Deluxe. Yep. So, what else has happened? Well, population has really took off in the post-World War II period. And in order to feed people, you need to grow more crops. And how do you do that? You use more pesticides and you use more fertilizer. Key component of fertilizer, nitrogen. All right? So what we see is the internal combustion engine and the increase in the use of fertilizers. And we're picking that up in the air that passes over the Greenland ice sheet in the North Atlantic. So in order to do the work that Lonnie and I have done over the years, and that our team, I want to stress this is a big team activity, has done, we have to have facilities. So I thought I'd just give you a sense of our facilities. So we use a Class 100 clean room. This is our clean room. The air's filtered, etc. And then we use a variety of equipment to measure dust. We'll use this Coulter counter to measure like the sulfate and the nitrate I showed you. We'll use an ion chromatograph. We measure black carbon with this SP2. We measure trace elements with a mass spectrometer here in a separate room. And we measure the oxygen and hydrogen isotopes with this Pacaro cavity ring down system, which we have too. But then, if you're going to work in the ice core business, you have to have freezers to store your cores. So these are the freezers that are on the back of the building in which we work. This shows the freezers themselves. We have 2 large rooms. We have 7,000 1-meter lengths of ice core collected from around the world, from high in the Arctic to actually 90 degrees south at South Pole, and from the Earth's highest glaciers. And then one thing that's unique about our group is that we design and fabricate our own drills. For Lonnie to be able to go to 22,000 feet, we can't take the same drills that we use in Antarctica, where we can go into our site with a C-130 or with a Twin Otter. And so our drills are very light, and we've spent a lot of time making them lighter. And also, I think, Lonnie, you're going to tell them more about the generators, and you'll have that. So we've had to really slim down the infrastructure that supports our work. So with that, I'm going to turn it over while Lonnie's coming up. This shows all the places on the planet where our team has drilled ice cores. Just want you to notice the high Arctic, the Antarctic, and then we say, and everything in between.
Thank you very much. It's a pleasure to have an opportunity to speak to you this afternoon. And I want to thank Bud Ward for the generous introduction and all the efforts he made to get us here. I've been fortunate in my career to be able to work in 16 different countries, 16 different cultures in order to do what we do. And it can be done without not only the team effort at Ohio State, but a global effort to make this happen. We forget sometimes we live on a sphere, but because we live on a sphere, 50% of the surface area is actually in the tropics. Between 30 north and 30 south, we have 7.5 billion people on the planet. 70% of them live in the tropics. So this is an area we need to know both natural and human-driven changes. A tropical glacier, this is the margin of Kilmarnock. You have a wet season and a dry season. This leads to this very distinct stratigraphy. Those are annual layers. So it's very easy to see how you can take a drill and recover a history in part of the world where we know nothing. So this is what makes the ice core drilling so unique. We have to have lightweight portable equipment, and we're very fortunate to live in a time when you have these types of technology that allow us to do this. And we have actually produced different types of solar-powered drills to recover the ice. And we also, in some parts of the world, because of the climate, you have to use diesel generators, and we have designed them so they'll actually run at 20,000 feet under very cold conditions. So there's a lot of technology that goes into making this possible. Then there's the logistics. How do you do this? If you're working over in Tibet, usually there are no roads going out to the mountain ranges, so you're going cross country, and you have to have a lot of support in order to make that happen. If you're at 20,000 feet in the Himalayas, you can use Sherpas and porters to carry these ice cores. But when you get down to the margin of the glacier, you're still 4,000 feet from where the freezer trucks can come out on the plateau, and then you have to use the local transportation. So if you're in the Himalayas, those are yaks. So these are insulated boxes, and each of those boxes there are 6 meters a core, 12 meters to a yak. We drill 600 meters a core, so you have to have a whole herd of yaks. And if any of you have a cat, the yak's temperament is just like a cat. It does not like to go where you want it to go. So we drove around the world, and I'm going to take you to the world's largest tropical ice cap. It's down in the Andes of Peru, right above the Amazon basin. So most people don't realize there's such masses of ice in the low latitudes. This is looking down a crevasse. You can see every dry season layer. If you go down into that crevasse, you can see that they're very uniform. And again, you can see if you can measure the thickness, you have precipitation. You can develop long-term history of precipitation. And there are very few archives on the planet that allow you to do that. This is what an ice core looks like coming from one of these. And this is, we measure, as Ellen was saying, about 15 different things. I'm not going to bore you with them. But how do you date a core? This is a period of time from 1805 to about 1825. We have annual cycle in isotopes, that's our temperature proxy. We have annual variations in dust. Measure the thickness of these layers and you can get precipitation. So you can reconstruct the history in the past and really look at where we are in a longer term perspective. So if you do that, this is the last 1,000 years, these are Cato averages. This was the first core drilled using solar power in 1983, and we didn't have technology to keep the ice frozen. So we came back in 6,000 bottled water samples that were prepared in the field. We went back 20 years later, after we had that technology, re-drilled the summit, which is his center profile, and the thing you can see here is the reproducibility of the record. The archive is really well preserved. So from 1,000 to about 1550 it was warm. Then we go into Little Ice Age when it was cold. Then the 20th century up here shows the warming taking place now. And because you have those distinct dust layers, you can look at precipitation. And if you look at precipitation, this first period was warm and dry, the brown you see here, followed by the onset of the Little Ice Age, which was wet and cold. Last part of the Little Ice Age was dry and cold, and the 20th century is wetter than normal. So this is how we get the history out of the ice. And we do this around the world. If you go to the Himalayas, this is the highest place ever drilled on Earth, 7,200 meters, 23,600 feet. And that's very difficult for human beings, I can tell you that. And that Shishapam in the background, it's an 8,000 meter peak in the Himalayas. But when you get the records back and you analyze them, just like in South America, you have this beautiful annual record in isotopes, in dust, and in nitrates, which is an indication of vegetation, in Nepal in this case. And you can go back in time and recreate a history. And if you do that, we have annual record here goes back 540 years. And you can see the increases in isotopes, increased temperatures, increase in nitrates and sulfates, and the anthropogenic input at the top of the core. But you can also see events in the past. And these were major El Niños. And because we live or work in the low latitudes, there are places where people live, and there's human records. For example, if you look in this 1878-77 period, this is a drawing from near Xinjiang, which is close to Beijing, where a mother is selling her children because of the droughts associated with that event. So you can go back in time in these areas. And because we work both in Tibet and down on the Altiplano in Peru, we can actually look at the long-term variations in things like El Nino which have huge impacts on the Earth's climate. And to give you an example of how that works, is that if you look at the isotopes in these tropical low latitude cores and compare them to our surface, sea surface temperatures measured, you can see that what we're really picking up in these ice cores is the El Nino 3.4 temperatures. And if you look on land, look at precipitation, this is down in Peru, but these are the major recent El Ninos, and it's dry, always on Calcaya in the south, and in the north of Peru, it's often wet, except for the most recent El Nino in 2015, 2016, when the whole Andes was dry. It was unusual around the world on its impacts. But in the ice, you can look and actually see the impact of that El Nino. This is 2015, 2016, in this last core here from Calcaya, and this is on Huascarán. And you see the lower accumulation that's associated with those events. So the ice is really recording those. But the other thing you can see in these records, this is our temperature profile. This is back in 1976, and you can see this annual cycle in the isotopes. And as you come forward in time with these cores, in 1991, for the first time, we saw melting occurring at this 19,000-foot summit. And by 2016, you can see this is a straight line. That's because water is moving through the pores, removing the signal. And we believe Huascarán is the last place in the Peruvian Andes where we may have an unaltered signal still being preserved in the glaciers. So if you look at these records across the Pacific, this is Dasupu, this is Corapuna, southern Peru, this is Calcaya, and you just look at the last 250 years. First of all, when we have El Ninos, India is dry, and so you get dust that blows off of the plain up to the Andes or the Himalayas. And if you're over in the Andes, there's a big high that sets here, it's dry, and the air circulates across the Solar de Uyuni, which you can see here, it's the largest salt flat on Earth. And what this means is that in a La Nina, the opposite cycle, this salt flat often has about 10 centimeters of water on it, but usually it looks like this. And if the wind blows, it looks like this, and that salt gets carried up on the glaciers, gets preserved. So you can use that to look at the past. And if you go back to a drought in the 1790s, we have good evidence this was caused by several very major El Ninos at that time. And if you look at the chloride, which is a record of the salts, in all these cores, 22,000 kilometers apart, you see the same event. And it started in about 1789 and went to about 1800. And then you can look at history. What was happening at that time? Well, if you were in India, it was the East India drought. 1791 was the center core of that. There were 11 million deaths during that period of time in India, 600,000 in 1792 alone. This is before India had 1.3 billion people. This is 200 years ago. So these are natural variations. There were severe droughts in Java, Australia, Mexico, Caribbean, Egypt. Same signal we get today during El Ninos. And there were great social upheavals around the world. We had 4 civil wars at that time. So, as Ellen was saying, if you look around the world, all these red areas are where we're losing ice. And you can see it's really big over here in what we call the third pole region, over in the Himalayas. And a number of years ago, a group of us got together up in Chicago, and we started a program called the Third Pole Environment Program. And the reason is that this area is very high and cold and remote, covers about 5 million square kilometers, one of the largest stores of fresh water, over 46,000 glaciers, and it is a source of water for many of the largest rivers in that part of the world. And it helps sustain about 1.5 million people in 10 different countries. And this program brings 14 countries together, many of them which do not get along in today's world, and trying to understand the science and the implications for the future in this part of the world. As part of this program, in 2015, we drilled over in the western Kunlun, and our goal here was to acquire the oldest ice in climate history from outside of the polar regions. And this ice field is unusual in its size and where its location. This ice field is located at the same latitude as Durham, North Carolina, so south of us. And so it's down at the latitude we live, and we can look at the history of the past. It has a marvelous record preserved in it, and you can see the reproducibility in the isotopes, which is a temperature proxy. But what makes it so unusual is that if you look at the dating of this core, we're using cosmogenic nuclides to do that, we can see events like the Le Champ event that we see around the world 41,000 years ago. But what really makes it unusual is that the bottom of this ice seems to be over 600,000 years old. So it would make it the oldest ice outside of the polar regions ever found on Earth. But what makes this program from a personal point of view very unique is that 3 years before this expedition, I had a heart transplant. So hospital at Ohio State University. And at one stage, I weighed 138 pounds. I had to learn to walk again. And but we live in a remarkable time in human history. And 3 years later, I set a world record for heart transplant patients by working at 22,000 feet. So it truly was remarkable in so many ways. One of the things we're worried about as we look at the future is surprises in the system. And we were drilling up here on Gallia. A year later, in 2016, down in the Argu Glacier site, we had 2 glaciers that collapsed. And this is a place where this is not known to happen. There are no historical records of it. But in the New York Times in 2018, they had this picture. The first one collapsed in July of 2016, killed 9 Tibetan shepherds, hundreds of yaks and sheep. And then 2 months later, another one just in the south collapsed. And this ice comes down out of the mountains traveling at 60 kilometers per minute. And there's no record of this occurring. So the question is why? And one of the things we believe is the temperatures in the Tibetan Plateau region. Here's that new Gallia core, and this is the last 2,000 years. And you can see the last decade, there's nothing like it for over 2,000 years. So we think these glaciers are becoming unstable in the current climate. And of course, if you look at the temperature reconstructions using isotopes of all the tropical glaciers, they show basically the same curve. If you compare it to northern hemisphere temperatures, you can see the medieval climate anomaly here in the low ice age. But what really stands out in these curves are the last 50 years, to give you this longer term perspective. But I can tell you, you can present this at the US Senate, they will glaze over, and you will get no response. But what they do respond to is the glaciers. As Ellen was saying, they are recorders, but they also respond to climate change. So I'm going to show you what's happening around the world very quickly. This is a quote from Henry Pollack's book, A World Without Ice. And it says, ice asks no questions, presents no arguments, reads no newspapers, listens to no debates, it's not burdened by ideology, carries no political baggage as it changes from a solid to a liquid, it just melts. So in some ways, it's a very strong indicator of change. So finding old pictures in some of these areas is difficult. We found this on a glass plate from the granddaughter of a photographer in Cusco. It was taken in the 1930s. And here is the same place, Kiririti, in 2006. This is the rock that he was sitting on. And you can see what's happened to glaciers. And if you overlap them, the gray areas are where the ice was, the white areas are where it is now. And you can see it's not only the area, the shrinkage, but they're thinning from the top down. So we're losing tremendous amounts of mass. I showed you this picture. I took this when I was a graduate student. This is what it looked like by 2002, same place. So it shows we're losing the history, but we're also losing a very valuable water resource for the people who live downstream from these glaciers. This is Koikalis. It's the largest outlet glacier. And I'm going to show you what it looked like a month ago when we went to this site. And it's truly amazing the change that has taken place in 40 years. The lake now covers over 81 acres. It's over 200 feet deep and did not exist before 1991. So it shows the change. Here's another part of that ice cap. Here's a boulder. You can see this ridge here. This is 1978. In the next photo you'll see last month. 40 years later, here's the boulder, here's that ridge, and here's the ice cap. And so all the ice in here has disappeared over that period of time. The ice cap, largest tropical ice cap on Earth, has shrunk by 30% since I was a graduate student. And another thing that's unique about this site is that this is 1977. This is now a lake. This is the backside of that lake in 2002. You see a person here of a scale. This whole wall, about 100 feet high, is retreating. And at the base of the wall, we found a wetland plant, 2 meters across, perfectly preserved. And we were able to collect that plant, have it identified, and we were able to date it. And it was 5,200 years old. So it took, the glacier had not been smaller for over 5,200 years, otherwise this plant would have decayed. Well, what's remarkable is how fast the glacier is retreating. This is that vertical margin in 2002. 3 years later, here's the plant, there's the vertical margin. And as it's retreated, more plants have come out. The oldest plant we've collected to date now dates 6,600 years in age. But to give you an idea of what you can do here is that in 1984, this lake didn't exist. The ice was out here. And all the plants collected over here were 4,700 years. In 2011, this island appeared. There were plants on that island that dated 6,300 years in age. So 6,000 years ago, it took 1,600 years for the ice to advance from here to here. It took 25 years for it to go from here to here. And what is remarkable, this is 2011, so 7 years later, last month, this is the same place. You can look at the island here, focus on that, and then here it is now. And you see the glacier is totally out of the lake, and it's just water, and we collected 10 more plants that were exposed, and they're currently being dated. But if you go to the Himalayas, you'll see the same picture. Here's a photo from 1921, same place in 2009. I don't know if any of you have been to Kilmarnock, very famous place. We actually drilled here in 2000. But these are the glaciers on the mountain. Here's the oldest photo. These are actually glaciers in 1912. This is not snow, it's ice. And coming up to 2006. And by 2013, we had lost 88.3% of the ice that had been present in 1912. And 40% of the ice that was present in 2000 when we drilled had disappeared by 2013. And I had a master's student who just finished, and by 2017, 90% of the ice that was present in 1912 has now gone. When we drilled the Furtwanger Glacier in the crater, we actually put a stake all the way to the bedrock. And that stake was measured just about every year from 2000 until 2013 when the ice disappeared from this site. So 2 of the sites where we drilled in 2000, the glaciers are now gone. So the ice is disappearing, and it's disappearing from the top down. This is Furtwanger when I first saw it in 1999. This is a crater rim, and to give you a perspective, this is what it looked like by 2017. The crater rim is over here. So these glaciers will disappear. Now, the last place I want to take you is New Guinea. Most people don't know that there's a glacier out there in the middle of the tropical rainforest. The oldest photo I could find was taken in 1936. And by 1991, it's broken into pieces. This is 2001. We drilled here in 2010. You can see the glacier is breaking up even at that time. The ice is 32 meters thick. We drilled here and up on this dome. But what is remarkable is what's happened since 2010. So this is a picture in 2010. And what you're going to see is this every 2 years going forward. Watch this and watch these holes develop in this glacier. So as we go forward in time, this was 2012. This is 2014. This is 2016. This is by March of 2018. And so you can look at the rate that this glacier has disappeared, and you can look at the first maps. And one of the questions we always get in the places we work is, when will this glacier disappear? And so if you look at where it was in 2010, this is what it looked like. This is 2018. And you look at all the maps that have been made. First let me just say what might be driving these changes. If you look at that projections of CO2 increase, say 800 parts per million by volume by 2100, that 3-degree warming projected from the surface is twice that at the high elevations in the low latitudes. And so if you look at these glaciers, if you look at, here's the one in the beginning, and if you look at the first map made in 1941, come up to the present, and you project the lines, you see it'll disappear by 2020. And if you look at Kilimanjaro and you do the same thing, and just connect the dots and project it out in the future by 2025. And Kilmarnock, the largest tropical ice cap on Earth, is along this trajectory, and so if you send it out by 2060, we would expect that glacier to be gone. So if you look around the world, ice is disappearing, and as Ellen was showing, the sea level is rising, and we have lost about 2,300 cubic miles of ice, and the sea level, that's equivalent to about 27 millimeters of sea level rise. And that is accelerating as we go forward in time. So what does that mean? If you were to lose 8% of the ice now on land, this is what our coastline would look like down in Florida. It's only 8% of the ice that's out there right now. We've already lost 30% of Kilmarnock. And we also see the impacts of this already. This is flooding from at high tide in Florida, in Miami. And if you talk to the mayor of Miami, there's no doubt that climate is changing on this planet. In Ohio, where we come from, 2011 was the wettest year on record. But if you look at the U.S. as a whole, and these are observed changes in very heavy precipitation, they're up 71% over this period from 1958 to 2012 in New England. Here we are in Virginia, they're up 27%, and over in Ohio, 37%. So this is a large-scale changes that are taking place. All you have to do is watch the nightly news to see these changes. These are fires. These are acres burned. And what's remarkable is how recent these years are when these acres have burned. And then if you come up to 2017, we had all of these events. Harvey, Houston. A month later, Hurricane Irma in Florida. And another month later, September, Puerto Rico, Hurricane Maria. And out west, we were having fires. This is Santa Rosa, before and after. And we have a history of acres burned in this country. So if you look at that, here's from 1960, this is the level, but you can see how they've jumped. And this goes up to 2017. So it's not, I mean, it's actually happening. We have good records to document these changes, and of course, they cost big bucks when this happens. And it's not just us, it's around the world. This past summer, this is July 2018, these are historic floods in Japan and high temperatures. Florence, in this part of the world, just a couple weeks ago. And then things that we don't think about. Only 10% had flood insurance. for this. The sewage problems that come from this, hog farm waste, toxic coal ash, 340,000 without power, 10,000 10,000 shelters across the state, 3.4 billion chickens dead, 5.5 thousand hogs. I mean, they impact everything in our environment. And so if you look at the extreme weather events in the Northern Hemisphere, here's a few of them, but it's just to point out that this is a global phenomenon. It's impacting everywhere. And then Michael that went through here, the impacts are still being assessed, but only about 50% had flood insurance, 1.5 billion without power, cost 25 billion, we don't know yet. It keeps going up every day. But these are real-time events. And the people who really watch these things are like Munich Re, Swiss Re, insurance companies that insure insurance companies to get a global distribution of risk. And these are their records of worldwide extreme weather catastrophes, from storms, floods, extreme temperatures, and you see how these are rising. So over the last 10 years, weather-related losses averaged about 155 billion a year. 40 billion was actually covered by insurance. That means taxpayers, or you, pick up the rest. And this brings home another human characteristic, behavior analysts. Immediate consequences outweigh delayed consequences. I think when it really starts costing big money, we start listening and being concerned about these changes. The cost of extreme weather catastrophes in 2017 in the U.S. alone was over 310 billion. This was a global number. This is just the U.S. last year. So these costs are likely to continue. If you look at where our largest cities in the world are located, more than half are on coastlines. Therefore, they're subject to sea level rise and storm-related problems coming from the oceans. And there are groups who look at what's going to happen if we get a 1 meter global sea level rise. This is the square kilometers that will go underwater. 145 million people would be displaced. These become migrants. And you can look at Syria and see how well we're dealing with migrants coming out of Syria. And the cost would be $944 billion. If it's a 5 meter sea level rise, you can see what the coastline of the U.S. would look like. But also, this is a global phenomenon. Bangladesh pretty much disappears, and you can see a lot of China gets flooded. So these are huge changes geography of the planet. So the other thing that we're concerned about are tropical diseases, and they're moving to higher altitudes and higher latitudes. When I look at our future in the 21st century, we have, I think, two great challenges. One is learning how to get along with each other on this planet. This is something we've dealt with ever since humans have been on the planet, and you can debate how well we do that. But the other part of this is learning how to get along with our planet. How do we maintain, sustain the life on this planet? And these are huge challenges, and they deal with human behavior and are closely related, both of these two items. So let me simply close by saying that we live in a special planet. You call it a Goldilocks planet if you like. Venus is too hot, Mars is too cold. We're perfectly positioned. And everything we know and depends on the climate of this planet. And when you talk about global climate change, nature is the timekeeper here. And none of us are wise enough to know how much time we have to make the changes that have to be made. But we do know the system is changing. We have evidence around the world. So I'm going to end with this view. This is our next drill site. This is Huascaran. It's the highest tropical mountain on Earth. And we're drilling here next summer. So thank you very much.
very briefly, one question always comes up is, what can I do about it? And the Thompsons have agreed, and I certainly agree, that there is one organization that is pretty effective in trying to do something about it. It's called the Citizens Climate Lobby. We have some material here about it. They champion an approach which they claim, with some justification, will appeal both to political conservatives and to political progressives. There's data suggesting that's indeed the case. It's called a tax and dividend program. There's some literature over here if you're interested in anything about CCL. There's a representative right back here. Raise your hand. So if anyone's interested in addressing the question, what can we do about it? It's a huge problem. I always like to say nothing's going to work, but a billion things might work. And I really believe that. If I change my light bulbs, it's not going to work, but if 4 billion of us, or 3 billion of us change our light bulbs, it might work. So CCL is one option. It's not partisan like some of the groups on left or right. So if you're at all interested, you can gather the literature from it.